So, in the previous chapters, we've discussed infrared spectroscopy and ultraviolet spectroscopy, as well as mass spectrometry. Now, in chapter 17, we are going to talk about nuclear magnetic resonance spectroscopy. Again, there are entire classes that are dedicated just to nuclear magnetic resonance spectroscopy. There are a lot of different types, and so we are just really going to scratch the surface here. So just kind of keep that in mind, that this is a really big field and that people can specialize just in this particular field of chemistry. Now, because of the information it provides, NMR, which is our abbreviation here, spectroscopy is generally considered one of the most powerful tools in organic chemistry for figuring out molecular structures. NMR can tell us the number of distinct types of hydrogen and carbon atoms in a molecule, as well as give the atom-specific environment. And that allows us to determine the connectivity of atoms within a molecule. So whereas mass spectrometry can tell us the molecular weight and IR can tell us the functional groups, this can give us a lot of clues into how the different pieces of the molecule are connected. And so just by comparison, IR isn't going to give us really any information about connectivity. Mass spectrometry provides a little bit, and of course UV-Vis doesn't provide any. So understanding NMR does require a grasp of principles that are somewhat more complex than those underlying IR or UV-Vis. And NMR often has more features to analyze than a typical IR or UV-Vis. So interpreting an NMR spectra is somewhat more involved, and that's why we're going to break it up over two different class periods. So just kind of keep that in mind as we go through this. And remember, we are going to do some examples in class, and you can always ask questions. So let's start with the instrument itself. The instrument itself, these are very expensive instruments. They are starting to develop some desktop NMRs that are about $40,000. But NMRs themselves can be up into the millions of dollars. Now, when we look at this, right, NMR spectra, so let's think. Let's compare NMR first to UV-Vis and IR. So we know that IR, right, uses radiation from the IR region, hence the name. That's very helpful. And then we know UV-Vis utilizes the ultraviolet and the visible regions of the electromagnetic spectrum. Well, NMR uses radio frequencies, or the radio waves part of the spectrum, and that is not in the name. So just, that's a little misleading, so don't let that surprise you. So radio frequency, also known as radio waves, and that's the electromagnetic region that it is involved in. Now, you're probably familiar with the radio waves because it's used in communication technologies like AM and FM radio signals, and then wireless network connections for computers. Now, photons in this range are less energetic than those for either the IR or the UV-Vis regions, encompassing frequencies that are right around 3 hertz to 3 times 10 to the 11th hertz. Most modern NMR spectrometers, however, work in a really narrow range. So while radio frequencies are a lot bigger, NMRs themselves work into about 10 to the 7th to 10 to the 9th hertz. And that's what we see there. A typical setup for an NMR is shown here, right? Basically, so if we look right here, we see a tube. This is a small glass tube, and you put a liquid sample in this glass tube here. And there's a little red cap there. It doesn't take very much to do an NMR, but you don't get the sample back. But you do need about 5 milligrams of the sample. It's dissolved in something called a deuterated solvent. And we're going to talk more about a deuterated solvent. It'd be helpful if I spelled it correctly. So let me... Now, a deuterated solvent, when we talk about this, the one that's most common is CdCl3. Remember, deuterium is just heavy hydrogen, right? So deuterium will have an additional neutron, right, to make it heavy hydrogen. And so what that means for us is because the NMR a lot of times picks up hydrogen signals, we need some sort of solvent that doesn't have hydrogen in it, so we don't have an overlap with hydrogen and whatever's in our solvent, okay? Because we want to keep that separate. Now, so it's placed in a glass tube. It's lowered into the hollow bore of a superconducting magnet, which is shown here. This is where the superconducting magnet is. And it's irradiated with a short pulse of radio frequency radiation that's emitted from the NMR probe here. Now, this probe delivers a range of frequencies produced by the RF generator, and as in any spectroscopic experiment, we want to attain a spectrum. And so this is what the spectrum is going to look like. That can tell us which of those frequencies are absorbed and how strong each absorption is. Now, what we're going to see here is on the x-axis. This is called a chemical shift. That's measured in parts per million, which is ppm. And then we see the signal amplitude here. We always have to set the signal, and we're going to talk about that in a second. So this is generally how an NMR works. If you have ever had an MRI, this is the exact same technology as an MRI. They just don't call it, nuclear magnetic resonance for MRIs, because at the time they were really worried that people would panic over the nuclear part. And so they changed it to magnetic resonance imaging, so people wouldn't be concerned that they were being exposed to nuclear radiation. And as you can see, there isn't any nuclear radiation in this. The nuclear here refers to the nucleus of the atoms that you're studying. So there's no radiation that's involved here. So we've talked a little bit about this, but I want to give you this is kind of a summary of the general setup, right? And we already spoke about this, but NMR spectroscopy uses radiation from the radio frequency, which is going to be abbreviated as RF region of the spectrum. It's also called radio waves, right? And NMR makes use of a superconducting magnet, which subjects the sample to a very, very high external magnetic field, okay? And that's the superconducting magnet. We get exposed to an external magnetic field, and that throughout this chapter is going to be abbreviated as B external, okay? When we talk about magnetism, a lot of times the symbol for that is B, and this is the external magnetic field. Okay, now we're going to have another magnetic field coming up, but just kind of be aware of that. Now, that is one of the big differences. The fact that we have an external magnetic field is one of the big differences between the typical setup for an IR or UV vis or a mass spectrometer versus an NMR. Now, the second way that there's a big difference is the way that each absorbed frequency is detected. In IR spectroscopy and UV vis spectroscopy, transmittance at a particular frequency or wavelength is obtained by comparing the intensity radiation that's passed through the sample to the intensity radiation of the source, okay? Now, so in those, we compared the intensity that was detected, right, because we're messing with light, to the intensity of the source. Well, there isn't any light here, so we're not going to deal with that. Instead, most NMR spectrometers are going to take advantage of the fact that a portion of the radio frequency radiation absorbed by the sample at each frequency is re-emitted at the same frequency. Now, the magnitude of the oscillating radio frequency radiation, and remember, oscillating just means it's moving in waves, okay? So that magnitude of oscillating radio frequency radiation that's emitted from the sample is recorded over a period of few seconds and digitized, producing what is called a free induction decay. Now, this is abbreviated as FID, okay? Many FIDs are typically acquired and are averaged, after which a mathematical algorithm called Fourier transform decomposes the FID into its individual frequencies called signals. Now, the amplitude of each signal let's pretend like I can spell amplitude correctly. Amplitude, DE, of each signal is proportional to the amount of radiation that was originally absorbed. Okay. So that recorded signal is converted automatically into a spectrum that's very similar to other spectra that we've seen, where you have a relative absorbance is plotted on the y-axis against a characteristic radiation on the x-axis. As I mentioned before, on the x-axis, what you're going to see is something called a chemical shift, which we're going to refer to. It is a lot of times abbreviated using the Greek letter delta, the lowercase Greek letter delta, and that's just a measure of the relative frequency. And now that's relative to a known that we set. The known that we use is tetramethylsilane, which is TMS. And we'll talk more about that in some future sections. And that chemical shift represents how much a particular signal frequency differs from the frequency of that reference compound, which is tetramethylsilane, which is TMS. Now, a few things. You all have, or maybe not all of you, but many of you have taken calculus. One of the interesting things about NMR is it was developed in the 1950s, and it's an application of calculus principles that didn't have any implied uses at the time. So one of the things that's particularly neat about that is people were researching this Fourier transform, and they had a lot of mathematical applications for it and algorithms, but they didn't have any practical applications. So this is an example where people were researching things where there weren't necessarily a known practical application, but as technology got better, we were able to apply this to a great practical application. NMR is one of our most powerful tools in chemistry. And then, of course, it led to magnetic MRIs, which is really kind of interesting. So with this overview of NMR spectroscopy in mind, we are going to ask several questions as we go through this. One is, why must a large magnetic field be applied to the sample? So all of a sudden we're messing with a magnet where we've never messed with that before. Why are only certain frequencies of RF radiation absorbed by a given sample? And then how can an NMR spectrum be used to interpret molecular structure? And so we're going to answer those questions as we look through different sections throughout this particular time. Okay, so let's first start off and say, all right, let's answer that question about the magnetism first, right, or that magnetic field. So in an NMR experiment, the sample is placed in a strong magnetic field because without being subjected to a strong magnetic field, a sample is not going to absorb RF radiation and cannot produce a NMR spectrum. Okay, so we can't get an NMR spectrum unless we use a magnetic field. Well, maybe the big burning question here then is why, right? Well, if you're acquiring an NMR spectrum and it's going to depend on the strong magnetic field, it depends on it because of nuclear spin. And so nuclear spin just describes the state of an atomic nuclei that generates a small magnetic field, okay? The same kind of field that would be produced from a spinning charge, okay? So what that means here is, hey, look, each of your nuclei, right, themselves have a small magnetic field that's associated with them. And we are looking here at hydrogen nuclei. And so the most common example here is that hydrogen atom, like a proton, and that spin's going to be analogous to an electron. So just as an electron can assume two spin states, a proton can also assume two spin states. It can have a spin up or a spin down. Now, what we do, so we have that 1/2 up or 1/2 down, right? And that corresponds to an alpha spin state and the beta spin state. So the spin up is alpha and the spin down is beta. So protons then, right, can generate a magnetic dipole in one of two ways. Right? And because of that, each proton behaves like a tiny bar magnet, which is why the image there shows you a tiny bar magnet, right? And remember, bar magnets have a north and south pole. So these nuclei a lot of times are represented as arrows that are indicating, right, their magnetic dipoles. So we have the arrow up, which is the alpha spin state, and then the arrow down, which is the beta spin state. Now, when there is no magnetic field present, like here, there is no energy difference between the alpha and beta spin states, right? So no energy difference. So a proton's either like equally likely to be in either state, right? They're just all over the place random. And magnetic dipoles of the proton, right, as we can see, are just pointing in random directions. Now, this is similar to what we would observe if we were to just grab several bar magnets and toss them on the floor, right? They just go in all sorts of different directions. Unless two of the magnets are close enough to affect each other, they end up with random orientations. But in the presence of an external magnetic field, that situation is different. So think about it. If you throw a bunch of bar magnets on the floor and they're just going to be in these random directions, but if you were to take another big magnet and move it over them, all of a sudden they're going to align, right? Or they're going to line up. So that's basically what we do in NMR is we have this big external magnetic field, which is that big external, that magnet that you saw in our very first slide, right? And when that's applied, then the nuclei line up, right? And the nuclei are either going to be aligned with the external field, right? And the alpha states align with the external field. And then the beta states align against the external field, okay? Now, the energy of the alpha state is slightly lower than the energy of the beta state, which is what there's energy here. That's what you're seeing. So the energy of the alpha state is lower than the energy of the beta state. And we can kind of think about this because it's kind of like if you're thinking about a current in a stream, these guys are swimming against the current, and it's a lot harder to swim against the current. You have a lot more, it takes a lot more energy. So we're going to be at a higher energy state there. These guys, we can imagine they're swimming with the current. And so if you're swimming with the current, it doesn't take near as much energy. Now, what's really interesting to us is this difference in energy between the alpha and the beta states. That's directly proportional to that external field. So, as that external field increases, so does the difference in energy between those spin states. Now, that energy difference is really, really important to us because if we look over here, right, the delta energy, that difference in the energy spin states corresponds to photon energies from the RF region of the electromagnetic spectrum. Okay, so that means that a nucleus in the alpha state can absorb an RF photon and be promoted to the beta state. Now, this is called a spin flip. Okay, so when we talk about a spin flip, what's happening there is an alpha spin state absorbs RF photon, right, and is promoted to the beta state. And that's what you're seeing here, right? Here comes the photon, there's the alpha, it gets real excited, it goes whoop, and jumps up there to the beta state. Now, it relaxes eventually back down, okay? So when the promoted proton in the beta state relaxes back to the alpha state, it's going to emit RF radiation. And when it emits that RF radiation, right? So when this happens, it's going to emit RF radiation. And when it emits that RF radiation, that's when an NMR signal is produced. Okay? So by now, you should be able to understand why we can't get an NMR spectrum if we don't have a magnet. Okay? So when the beta state returns to the alpha state, RF photons are given off, and that signal can be detected. And the signal appears as a peak in the NMR spectrum. And so because of this, RF radiation can be used to study the nuclei of protons. Now, Most of this chapter is going to focus on proton NMR spectroscopy. We are looking at the protons, and it is called, we talk about proton NMR spectroscopy. It's abbreviated as that proton H1 NMR. Right? And that's what's happening there, of course, is the RF radiation causes spin flips in the nuclei of the hydrogen atoms. Now, NMR spectroscopy can also be used to probe other nuclei that produce spins, and these are called NMR Active Nuclei. Okay? So in general, a nucleus that's NMR active can be studied in NMR spectroscopy if it has an odd number of protons, right? Or an odd number of neutrons, or both, okay? So if we think about this, this is consistent with the proton being NMR active because its nucleus just has one proton, which is an odd number. Deuterium is also NMR active because its nucleus has one proton and one neutron, and those are both odd numbers. So deuterium, right, which we briefly mentioned there, is also NMR active. It just gives a signal at a different area. But the carbon-12 nucleus has 6 protons and 6 neutrons, is not NMR active. So we can't study carbon-12 we just can't study carbon-12 in organic molecules. However, we can study carbon-13 because carbon-13 has an odd number of neutrons. And so the second part of this chapter is going to be about carbon-13 NMR spectroscopy. So in this chapter, we're going to look at proton spectroscopy at the beginning and then carbon-13 spectroscopy towards the end. Now, there are other nuclei you can look at. You can look at nitrogen 14, you can look at nitrogen 15, you can look at oxygen 17, you can look at fluorine 19, and you can look at phosphorus. And so you can look at lots of different other other atoms in NMR. But for us, at least, in organic chemistry, we are really just more interested in the hydrogen and the carbons that are associated with it. Now, if you get into more complex biochemical principles, that's where phosphorus becomes really helpful, as well as nitrogen, right? So if you think about your DNA and RNA complexes, there's a lot of phosphorus and nitrogen there in those complexes. So these are really used for some biochemical principles, whereas we're going to stick to proton NMR and carbon NMR for organic chemistry principles.